Good morning, students. Krishi sir again with an interesting question in rotation. So today we are going to discuss a bicycle going up an inclined plane with uniform velocity. Here are my credentials. You already must be knowing it. So we are talking about a bicycle going up an inclined plane. As you see in the diagram, it's an inclined plane. A bicycle is going up the inclined plane with a constant velocity, uniform velocity. There is a rear wheel, which is driving wheel, because the sprocket is connected here, chain sprocket connection here. The rider is pedaling here. So the torque, driving torque is applied at the rear wheel. Front wheel is just a supporting wheel. Okay. Angle of inclination theta. And there is no slipping between the wheel and the inclined plane. Exactly, that's the detail I have written in the question. You can see bicycle is going up on inclined plane with a uniform velocity v. There is no deformation of the wheels and the inclined plane. So there is no deformation of the wheel. They maintain their circular shapes, cross sections, and there is no deformation in the inclined plane as well. So by this, what do you mean? There won't be any rolling friction. Whatever friction will be there, that will be the sliding friction or the static friction between the inclined plane and the wheels. If it slides, it becomes a sliding friction. If it does not slide, just rolls up, which is the case right now, it's just a static friction force. But there is no rolling friction because there is no deformation of either the wheel or the inclined plane. Keep it in mind. Okay. So the wheels roll without slipping. So there is no slipping between the touching point of the wheel and the inclined plane. Friction exists only between the wheel and the inclined plane. There is no friction at the axle. There is no air friction. Only friction force exists between the inclined plane surface and the touching point of the wheels. That is the only thing you have to see. Okay, the weight of the bicycle, including the rider, is W. Angle of inclination is theta, as shown in the diagram. You can see theta angle of inclination, and the weight is the W for the whole rider plus bicycle. The question is, what is the frictional force acting on both the wheels? How much friction force is acting on both the wheels? Very clear. So let us see the solution. Since the bicycle has no acceleration because it's moving up with the incline, moving up the inclined plane with uniform velocity, so the net force on the bicycle along the inclined plane is zero, obviously. If there is no net force, there is no acceleration. Let F1 and F2 be the friction force on the rear and front wheel respectively. Just see the diagram which are drawing here. This is F1, this is F2. I'm showing because it's going up the incline. So driving this torque will be clockwise. This rider will be applying a torque clockwise through the sprocket of the rear wheel. So touching point will try to move back. So friction force acts up. So then what happens to the front wheel? This front wheel is just the supporting wheel pushed forward by the frame. The frame is connected to the front wheel, the frame of the bicycle, and that pushes it up. It has no torque being applied by anybody on the front wheel. Okay. So by the frame, the bicycle front wheel is pushed up and the frame is connected at the central axle of the front wheel. Okay. So obviously then F1 vector plus F2 vector. These are the two friction force vectors acting on the front wheel and the rear wheel. I've shown the F2 on the rear wheel to be the backward. If you want to take forward, you can take clearly. Plus W sine theta. W sine theta is the sine theta component which acts down the incline. So W sine theta plus F1 plus F2 should be 0, because in this along the inclined direction there is along the inclined plane the A is 0. That's why we can write like this. Agreed? Okay, now come to the force diagram of the front wheel. This is the front wheel. Radius R, O2 is center. The Fx, Fy, these are the two forces. The component of the forces which is due to the pushing action of the frame is pushing it up. Well, if I resolve the component of those forces, that is Fx, Fy, but both act at the O2. Then M2 is the mass of the front wheel, so M2G will be vertically down but passing through the O2. Fx, Fy, M2G, both all the three pass through the O2. Then N2, normal reaction force coming to the front wheel from the inclined plane is normal to the inclined plane, means it passes through the O2 again. So O2, I take the geometric center as well as the center of mass of the front wheel. You can say uniform front wheel. You can say there are some spokes will be here, some spokes. Obviously, those details I have not shown. So like this. Okay. So then let us calculate the torque about O2. So taking torque about O2 due to all the forces, we find Fx, Fy, M2G, I think that is M2 I have taken, so I better write M2G, and N2, they produce no torque about O2. Why? As all of them pass through O2. Very simple. This is a basic concept of the torque. If the force passes through a point, cannot produce any torque about that point. So which force is left out? F2. F2 does not pass through O2, so it can produce a torque about O2, as since I have shown in the down the inclined direction, so it will produce a torque clockwise manner about O2. That's what I have written here. So only frictional force F2 produces torque about O2, and that torque is given by F2R clockwise manner. Had you taken F2 up the incline instead of down the incline, had you taken it up the incline, then torque O2 would have been in anti-clockwise manner. That's what you can know. So, since for the, if I choose my axis of rotation at the center of the front wheel, then what will I say? F2R, the torque will be equal to I O2Z into alpha. You know this. Torque about axis of rotation is I axis of rotation into angular acceleration. Are you observing? Okay. Okay. So here F2R, that is clockwise direction, is IO2Z into alpha clockwise direction. Alpha is the angular acceleration of the wheel. This I can always write because this is only unbalanced torque. So unbalanced torque along the axis of rotation. So that must be equal to axis of rotation. If I place myself on the bicycle, I'll see IOZ, O2Z as the axis of rotation of the front wheel. So axis of rotation into alpha, I about axis of rotation into alpha is F2R. Understood this? Right. But we have given then the question that the bicycle is going up with uniform velocity. Yes or no? So what is the acceleration of the wheel center? A2 will be 0. It is moving with uniform velocity. So if AO2 0, then alpha R must be 0. Alpha is the angular acceleration. Alpha is the angular acceleration of the wheel. So alpha R 0 at A of O2 0 means A of the center 0 means, so alpha R 0 because AO2 is alpha R in pure rolling condition. So then if it is 0, then R is not 0, then alpha must be 0. Then from going to the equation 2, if alpha is 0, then F2R also will be 0. But R is not 0, so F2 must be 0. Very simple observation. So friction force on the front wheel turns out to be 0. Surprising, but true. This is valid only when the bicycle is going up with uniform velocity. Then equation 1, what we wrote, equation force balance, total force balance. F1 bar plus F2 bar plus W sin theta bar is null vector. F2 bar we found out to be null vector. So F1 bar plus W sin theta bar must be null vector. Yes or no? That's one. F1 bar plus W sin theta bar is the null vector. Since W sin theta acts down the incline, of course, that gravity force on the bicycle plus rider will act down the incline. One component, that is W sin theta. But F1 plus W sin theta 0 means F1 must be minus W sin theta, that will be up the incline. So frictional force on the rear wheel will be W sin theta in magnitude acting in the up the incline direction. Okay. And no friction force acts on the front wheel. So the total friction force comes onto the rear wheel or driving wheel. That's what I have written here. That's why I try to correlate why the rear wheel wears out faster than the front wheel. You must have noticed. I hope you have noticed in the bicycle. In the above example, the total friction force acts on the rear wheel only, which is the driving wheel. That's it. Very simple question, very simple observation, but many of the people get confused. Some people say friction force should be shared between them equally and all this, but that's not true. Okay. So did you understand this? The whole thing is very important for us. Did you understand this? Yes. So this is a very interesting question. Obviously, rotational dynamics, very common in our day-to-day life. So I think you have got good concept now in this discussion. I'll come with some other typical conceptual discussions in my next video. Share my videos and subscribe to my channel so that you can know when the new videos are coming up. Right? Okay, we stop here. Good day to all of you.